Welcome back to the channel, fellow knowledge seekers. Today, we're diving deep into the fascinating world of physics. Get ready for an exciting exploration of the universe and its fundamental laws. We'll be tackling a topic that has puzzled physicists for decades, the quest for a unified field theory. Our journey will take us through the groundbreaking work of scientific giants like Isaac Newton and Albert Einstein. By the end of this video, you'll have a newfound appreciation for the elegance and complexity of the universe. Let's unravel the mysteries of the unified field theory together. Imagine a single, elegant theory that could explain all the forces and particles in the universe. That's the dream of a unified field theory. From Einstein's quest for a unified field theory to modern string theory, we'll cover the major milestones in this ongoing scientific adventure. Why is a unified field theory so important? Such a theory could unlock some of the universe's deepest secrets. So, whether you're a seasoned science enthusiast or a curious beginner, join us as we explore the quest for a unified field theory. Our journey begins with a familiar name, Sir Isaac Newton. Newton, a brilliant mathematician and physicist, sets out to explain the motion of objects, both on Earth and in the heavens. His groundbreaking work, published in 1687, laid the foundation for what we now call classical physics. Newton's laws of motion described the relationship between an object, the forces acting upon it, and its motion. These laws, elegant in their simplicity, could explain everything from the fall of an apple to the orbit of the moon around the Earth. Newton's work didn't stop there. He also developed the law of universal gravitation, which explained the force that attracts any two objects with mass. The impact of Newton's work on our understanding of the universe cannot be overstated. It provided a framework for understanding the physical world, a framework that would remain largely unchallenged for over 2 centuries. Fast forward to the early 20th century. A young patent clerk named Albert Einstein was about to shake the very foundations of physics. In 1905, Einstein published his theory of special relativity. This revolutionary theory proposed that space and time were not absolute, but were relative to the observer's motion. 10 years later, Einstein completed his masterpiece, the theory of general relativity. Instead of viewing gravity as a force, Einstein described it as the curvature of space-time caused by the presence of mass and energy. Imagine a bowling ball placed on a trampoline, causing the fabric to sag. That's similar to how mass warps space-time, according to Einstein. General relativity predicted the bending of starlight around massive objects, a phenomenon later confirmed by observations. It also provided the framework for understanding the evolution of the universe on the grandest scales, leading to the development of modern cosmology. While Newton's and Einstein's theories brilliantly explained the motion of planets, stars, and galaxies, a new realm of physics was emerging in the early 20th century, the realm of the very small, the world of atoms and subatomic particles. Experiments revealed that atoms, once thought to be indivisible, were actually comprised of even smaller particles, electrons orbiting a nucleus made up of protons and neutrons. Classical physics, it seemed, was reaching its limits, unable to penetrate the mysteries of the quantum realm. As physicists delved deeper into the microscopic world, they encountered phenomena that defied explanation within the framework of classical physics. A new kind of physics was needed, one that could account for the strange and counterintuitive behavior of the quantum realm. One of the key experiments that ushered in the quantum revolution was the study of black body radiation. Classical physics predicted that the intensity of radiation emitted by a heated object should increase infinitely as the frequency of the radiation increased. However, experimental observations contradicted this prediction. In 1900, Max Planck proposed a radical solution to this puzzle. He suggested that energy, instead of being continuous, was quantized, meaning it could only exist in discrete packets, or quanta. This groundbreaking idea laid the foundation for quantum mechanics. One of the most profound and unsettling principles of quantum mechanics is Heisenberg's uncertainty principle, formulated by Werner Heisenberg in 1927. This principle states that there are fundamental limits to the precision with which certain pairs of physical properties, such as position and momentum, can be known simultaneously. Imagine trying to determine the position and speed of a tiny particle, like an electron, with absolute certainty. According to Heisenberg, the very act of measuring one property inevitably affects the other. This inherent uncertainty is not due to any limitations in our measuring instruments, but is a fundamental feature of the quantum world. Heisenberg's uncertainty principle suggests that at the most fundamental level, nature is inherently probabilistic, not deterministic. Another bizarre and fascinating aspect of quantum mechanics is the concept of superposition. According to this principle, a quantum system can exist in multiple states simultaneously until a measurement is made, forcing it into a definite state. This seemingly paradoxical idea is perhaps best illustrated by Erwin Schrödinger's famous thought experiment involving a cat. Imagine a cat placed inside a sealed box along with a device containing a radioactive atom. The atom has a 50% chance of decaying within an hour, according to quantum mechanics. Until the box is opened and an observation is made, the cat exists in a superposition of states, both alive and dead simultaneously. Schrödinger's cat thought experiment highlights the strangeness of the quantum world and the challenges in reconciling it with our everyday experience. So far, we've journeyed through two seemingly different universes. We've explored the familiar world of classical physics, where objects move in predictable paths, like planets orbiting the sun, all governed by Newton's laws of motion and Einstein's refinements. We've also delved into the bizarre realm of quantum mechanics, where particles like electrons can be in multiple places at once, and the act of observation shapes reality. Classical physics offers a deterministic view, where the past dictates the future with clockwork precision. Quantum mechanics, on the other hand, introduces an element of randomness and uncertainty into the picture. This clash between the deterministic and probabilistic views of reality lies at the heart of the challenge in unifying classical and quantum physics. The contrast between classical and quantum physics goes beyond just determinism versus probability. Classical physics describes a world of continuous, smooth changes. Quantum mechanics, however, introduces the concept of quantization. Energy, momentum, and other physical quantities are no longer continuous, but can only take on discrete values, like rungs on a ladder. This quantization of energy and other properties has profound implications. The challenge in unifying classical and quantum physics lies in reconciling these fundamental differences in their descriptions of reality. Determinism versus probability, continuous versus quantized properties. Despite their apparent contradictions, classical and quantum physics are not mutually exclusive. Classical physics provides an excellent description of the macroscopic world, the world of everyday objects and phenomena. Quantum mechanics, on the other hand, governs the microscopic world, the realm of atoms, electrons, and other subatomic particles. The challenge lies in the middle ground, where the macroscopic and microscopic worlds meet. The search for a unified theory, one that seamlessly blends classical and quantum physics, is one of the greatest challenges in modern physics. One promising approach to unification is quantum field theory, which combines quantum mechanics with special relativity. Quantum field theories have been remarkably successful in describing the behavior of elementary particles and the fundamental forces of nature, except for gravity. Another promising candidate is string theory, which postulates that the fundamental building blocks of the universe are not point-like particles, but tiny vibrating strings. The quest for a unified theory is still ongoing, but the pursuit itself has already yielded profound insights into the nature of reality. It's a journey into the unknown, driven by the insatiable human desire to understand the universe and our place within it. Section 1. The Unification Dream, a Century in Pursuit. The quest for a unified field theory isn't a new idea. It's been a driving force for theoretical physicists for over a century. The dream is to find a single, elegant framework, a theory of everything. Physicists yearn for a single set of equations that encompasses all forces. James Clerk Maxwell united electricity and magnetism into electromagnetism. Albert Einstein dedicated much of his later life to searching for a unified field theory. However, the mathematics proved incredibly challenging, and Einstein's dream remained unfulfilled. Einstein's unfinished symphony, gravity's quantum challenge. Why is unifying gravity with the other forces so difficult? The problem lies in the fundamental differences between how general relativity and quantum mechanics describe the universe. General relativity, Einstein's masterpiece, describes gravity as the curvature of spacetime caused by the presence of mass and energy. Imagine spacetime as a giant trampoline. A massive object, like a star, creates a dent in this fabric, and other objects, like planets, move along the curved paths created by this dent. It's a beautiful and intuitive picture of gravity. Quantum mechanics, on the other hand, describes the universe in terms of probabilities and quantized energy levels. Particles don't follow well-defined paths, but exist as clouds of probability, and their interactions involve the exchange of discrete packets of energy. The challenge arises when we try to apply quantum mechanics to gravity. Attempts to quantize gravity, to describe it in terms of particles or gravitons and their interactions, lead to mathematical inconsistencies and infinities. The very fabric of space-time, smooth and continuous in general relativity, becomes a turbulent, foamy mess at the quantum level, making calculations, well, impossible. Despite the challenges, physicists haven't given up on the unification dream. One of the most promising candidates for a unified theory is string theory. String theory posits that everything in the universe is made up of tiny, one-dimensional vibrating strings. These strings vibrate in different modes, giving rise to the particles we observe, including gravitons. String theory is mathematically elegant and has the potential to unify all the fundamental forces. However, it also comes with its own set of challenges. It requires extra spatial dimensions, and its predictions are difficult to test experimentally. Nevertheless, string theory remains an active area of research, offering a tantalizing glimpse into a deeper level of reality. The search for a unified field theory is a testament to the power of human curiosity and our relentless pursuit of understanding the universe. While a complete theory of everything remains elusive, the pursuit itself has already yielded profound insights. It has forced physicists to confront the limitations of our classical intuition, to embrace the weirdness of the quantum world, and to develop new mathematical and conceptual tools. The unification dream continues to drive research in areas such as string theory, loop quantum gravity, and other approaches to quantum gravity. Each new theoretical development, each experimental breakthrough, brings us closer to unraveling the universe's deepest secrets. The quest for a unified field theory is not just about finding equations. It's about understanding the fundamental nature of reality itself. It's about answering some of the biggest questions humanity has ever asked. What are we made of? How did the universe begin? What is the fate of the universe? The journey continues, driven by the spirit of exploration, the thirst for knowledge, and the unshakable belief that the universe in all its complexity and beauty can be understood. As we conclude our journey through the vast landscape of physics, from falling apples to quantum mechanics, the universe is a symphony of particles, forces, and fundamental laws. Classical physics describes the dance of planets and stars, while quantum mechanics reveals the hidden world of atoms. Yet, the symphony is unfinished. We're still waiting for the final movement to harmonize these realms into a unified theory. The quest for unification is one of modern physics' greatest challenges. Imagine the thrill of hearing that final movement. It would be a profound revelation about the universe. The search for a unified field theory is a journey without a guaranteed destination. Driven by curiosity, we seek to understand the world, from the smallest atom to the largest galaxy. The journey is filled with wonder, discovery, and the joy of exploration. Remember, The universe is your classroom. Never stop asking questions, never stop seeking answers. Read, watch, engage. Every new piece of knowledge brings you closer to understanding the grand symphony of existence. Like, subscribe, and share this video. Let's inspire others to join us on this incredible adventure. Thank you for watching, and keep those curious minds engaged.